What was Earth's first apex predator? In our last episode, you discovered why trilobites dominated Paleozoic oceans for 270 million years. Their versatility, adaptability, and sophisticated anatomy made them unstoppable for most of the early animal era. But trilobites didn't thrive in a vacuum. They lived in ecosystems with predators creatures that drove the evolutionary arms race, making armor, eyes, and defensive strategies necessary. This episode focuses on the apex predators of the Cambrian Anomalocaris and its relatives. You'll discover how the first true hunters evolved, what made them so formidable, and why predation itself was the most revolutionary innovation of the Cambrian explosion. Picture this: you're a trilobite crawling across the Cambrian seafloor, searching for food among the sediment. Your compound eyes provide excellent vision across a wide field. Your armor protects you from most threats. You've survived for millions of years using this simple, effective strategy. Then you see something that shouldn't exist. A shadow passes overhead, huge, fast, purposeful. You instinctively curl into a defensive ball, pulling your head and tail shields together. But it's too late. Two massive grasping arms covered in spines seize you from above. They're powerful, flexible, and relentless. You're pulled upward toward a circular mouth rimmed with crushing plates. The mouth constricts around your shell, applying pressure your armor wasn't designed to withstand. You've just met Anomalocaris' first apex predator. For 3 billion years, life existed without true predation. Organisms absorbed nutrients, filtered particles, or grazed on microbial mats, but they didn't hunt. The Cambrian changed that forever, and Anomalocaris was the ultimate expression of this new, violent reality. Anomalocaris could reach 1 meter in length, the giant in Cambrian seas, where most animals measured only centimeters. It had the most advanced eyes of its time, powerful grasping appendages, and a unique mouth structure designed for processing prey. It swam with grace and speed, hunting in the water column with sophisticated sensory systems guiding every move. Nothing could threaten Anomalocaris. It sat at the top of the food chain, the undisputed master of Cambrian oceans. How did such a predator evolve? What did it look like internally? How did it hunt? And why did it ultimately disappear? The story of Anomalocaris is the story of predation itself, how hunting transformed life and set the stage for every ecosystem that followed. Evolution from filter feeder to apex hunter. How did predation evolve? The journey from passive feeding to active hunting required multiple innovations happening in sequence. The pre-predation world, before Anomalocaris, feeding was simple. Organisms either absorbed dissolved nutrients through their skin, filtered tiny particles from water, grazed on bacterial mats or algae, scavenged dead organic matter. None of these strategies involved actively capturing and killing other organisms. Why not? Because the anatomical tools for predation, jaws, grasping appendages, sophisticated senses didn't exist yet. Step 1. Grasping appendages. The first breakthrough was developing appendages capable of manipulating objects. Early arthropods had simple legs for walking, but some lineages evolved modified front legs with enhanced joints, stronger muscles, and eventually spines or claws. Why would walking legs evolve into grasping arms? probably through intermediate functions. Modified legs might have helped manipulate food items, hold onto surfaces in strong currents, or handle mating. Once grasping capability existed, natural selection could refine it for predation. Anomalocaris took this to the extreme. Its grasping appendages weren't modified legs. They were entirely separate structures extending from the head, specifically evolved for seizing prey. Step 2. Sophisticated vision. Predation requires finding prey, tracking movement, and judging distance. This demands advanced vision. Anomalocaris had the largest and most complex eyes of the Cambrian age, eye containing up to 16,000 individual lenses arranged in a stalked compound eye. How did such eyes evolve? Through gradual improvements in earlier, simpler eyes. The first eyes were probably just light-sensitive patches detecting shadows useful for avoiding predators or finding well-lit feeding areas. Over time, these patches evolved into cup-shaped structures focusing light, then into lens-covered organs forming images, and finally into compound eyes with multiple lenses providing wide-field high-resolution vision. Anomalocaris represents the culmination of this progression. Eyes so sophisticated they rivaled those of modern dragonflies or mantis shrimp. Step 3. Mouth structures for processing prey. Grasping prey is only useful if you can eat it afterward. Anomalocaris evolved a unique mouth ring of overlapping plates that could constrict and expand, creating suction and applying crushing force. This mouth structure was unprecedented. It wasn't jaws, which evolved much later in vertebrates, and it wasn't a beak like modern cephalopods. It was something entirely unique, a radial mouth with contractile plates. How did it evolve? Possibly from simpler circular feeding structures used for suction feeding on soft substrates. As prey became more active and defended, the mouth plates became harder, more precisely arranged, and capable of greater crushing force. Step 4. Swimming capability. To hunt effectively, Anomalocaris needed mobility. Its body was flanked by flexible lateral lobes, overlapping segments that undulated in waves, propelling it forward. This swimming method, called lift-based locomotion, generates forward thrust through coordinated lobes, creating hydrodynamic lift. Modern cuttlefish and rays use similar mechanisms. The evolution of efficient swimming was crucial. It allowed Anomalocaris to patrol large areas, pursue fleeing prey, and maintain position in currents while hunting. The Anomalocaridiid family, Anomalocarides, wasn't alone. It belonged to a family called Anomalocarididea, group of related predators showing variations on the same basic body plan. Anomalocaris canalensis, the classic species, about 60 to 100 centimeters long, with robust grasping arms and powerful build. Amplectobulua, smaller species with thinner, more delicate grasping arms, possibly specialized for catching soft-bodied prey. Herdia had an elaborate head structure with a large carapace, shell-like covering, possibly for hydrodynamic efficiency or protection. Petoia, formerly Ligania, had different mouth structure, possibly a filter feeder or scavenger rather than an active predator, showing that even within this predatory family, dietary niches diversified. The family appeared in the early Cambrian and persisted through the Middle Cambrian, roughly 20 to 30 million years of dominance before declining as other predators evolved. Anatomy built for the hunt. Let's examine Anomalocaris in detail every feature designed for predatory success. External anatomy, the perfect predator, body structure. Anomalocaris had a long, segmented, laterally compressed body, meaning it was flattened side to side, like a ribbon, rather than top to bottom, like a flounder. This shape reduced drag during swimming. The body consisted of 11 to 13 segments. Exact number varied by species and individual. Each segment bore a pair of lateral lobes, flexible overlapping flaps extending outward. These lobes were the swimming apparatus, undulating in coordinated waves that propelled Anomalocaris forward. The segments themselves were flexible but not heavily armored. Anomalocaris had a tough outer cuticle but not a mineralized exoskeleton like trilobites. This kept it relatively lightweight and agile. The head, sensory and predatory hub. The head was disproportionately large, housing the brain, eyes, and feeding structures. Eyes, two enormous stalked compound eyes, sat on the sides of the head. Each eye roughly the size of a large grappy, enormous relative to body size. Each eye contained up to 16,000 armatidia individual lenses arranged in a hexagonal pattern. The stalked structure allowed the eyes to move independently, useful for tracking prey while swimming in a different direction. The sheer number of lenses provided exceptional visual acuity and motion detection. Modern studies suggest Anomalocaris could detect movement from significant distances and had some depth perception through binocular overlap in the forward visual field. Some fossils preserve the internal structure of the eyes, revealing that they worked like modern compound eye-stitch lens, capturing a pixel of the image, with the brain combining all pixels into a complete picture. Grasping appendages extending forward from beneath the head were two large, segmented appendages about 1/3 the body length. These weren't legs, they were specialized predatory organs. Each appendage consisted of 10 to 14 segments connected by flexible joints. The inner surface bore multiple pairs of long, sharp spines arranged like the teeth of a comb. These spines curved inward and backward, perfect for gripping struggling prey. The appendages were muscular and flexible. They could extend forward to seize prey from a distance, curve inward to hold victims, and retract to bring food to the mouth. Fossilized appendage movements suggest they could move independently, one arm holding prey while the other struck additional targets, or both working cooperatively for larger victims. The mouth sat centrally on the underside of the header. Circular structure about 2 to 3 centimeters in diameter, smaller than you might expect for such a large predator. It consisted of 32 overlapping plates arranged in 4 concentric ringsate plates per ring. Each plate was hard, curved, and slightly toothed or ridged. The plates could slide over each other, allowing the mouth to constrict, becoming smaller and tighter, or expand, opening wider. This design created a powerful gripping and crushing mechanism. When Anomalocaris brought prey to its mouth, the plates would constrict around the victim, applying pressure from all sides simultaneously. For soft-bodied prey, this would crush them into digestible pulp. For armored prey like trilobites, the plates would apply force, trying to crack the shell. Interestingly, some fossilized trilobites show crescent-shaped bite marks matching Anomalocaris' mouth dimensions, direct evidence of predation attempts. Some marks show healing, meaning the trilobite escaped after being bitten. The tail, at the posterior end, Anomalocaris had a fan-shaped tail, 3 lobes arranged like a 3-pronged fork. This structure provided steering and could be flexed to change swimming direction rapidly. The tail wasn't particularly powerful for propulsion. That job belonged to the lateral lobes. But for maneuvering during hunting pursuit, the tail was essential. Internal anatomy, the systems behind the predator. Digestive system, the mouth opened into a short esophagus, leading to a relatively simple gutter, straight or slightly curved tube running the body length from head to tail. Why so simple? Because Anomalocaris probably consumed mostly soft-bodied prey that didn't require extensive digestion. The mouth did most of the mechanical processing, crushing and grinding prey into slurry before swallowing. Some scientists think Anomalocaris might have had digestive enzymes in its gut to break down proteins and other compounds. But without preserved soft tissue, this remains speculative. The anus opened near the tail, expelling waste. Circulatory system. Like other arthropods, Anomalocaris had an open circulatory system. A dorsal tubular heart ran along the back, pumping hemolymph forward through simple arteries. The hemolymph then flowed through body cavities, bathing organs directly before returning to the heart. The hemolymph likely contained hemocyanin for oxygen transporter, copper-based molecule that turns blue when oxygenated. When Anomalocaris died and its hemolymph oxidized, it might have been blue, though this is purely speculative. Nervous system. Anomalocaris had a relatively large brain for its time, necessary for processing complex visual information, coordinating swimming movements, and executing hunting strategies. The brain sat in the head region, with large optic lobes processing the massive amount of data from the compound eyes. From the brain, a ventral nerve cord extended through the body, with paired ganglia in each segment controlling the lateral lobes. The nervous system had to coordinate multiple systems simultaneously. Eyes tracking prey, appendages positioning for capture, body adjusting swimming angle, mouth preparing to receive food. This required sophisticated neural integration of evidence that predation drove brain evolution. Respiratory system. Anomalocaris lacked specialized gills visible in fossils, suggesting respiration occurred through the body surface and possibly through the lateral lobes. As Anomalocaris swam, water flowed over the lateral lobes and oxygen diffused through the thin cuticle into the hemolymph. The constant swimming provided continuous water flow, maintaining oxygen supply. This system worked because Anomalocaris was active. Swimming generated the water flow needed for respiration. Sedentary life wasn't an option. Anomalocaris had to keep moving to keep breathing. Musculature, powerful segmental muscles ran along the body, contracting in waves to undulate the lateral lobes. These muscles were the engine of Anomalocaris' swimming, generating the force that made it one of the fastest swimmers in Cambrian seas. Additional muscle groups controlled the grasping appendages, sophisticated arrangements allowing the complex movements needed for capturing struggling prey. Size. Giant of the Cambrian, Anomalocaris canadensis reached approximately 60 to 100 centimeters in length, though fragmentary fossils suggest some individuals may have approached 120 centimeters. This made it by far the largest animal in Cambrian seas. Most contemporaries measured only 2 to 10 centimeters. Why did Anomalocaris grow so large? Several factors. Predatory advantage. Larger body size allowed attacking a wider range of prey and deterred smaller predators. Swimming efficiency. At larger sizes, swimming becomes more energetically efficient due to favorable scaling of body volume versus surface area. Lack of competition in the early Middle Cambrian. Few other predators existed capable of challenging without competitive pressure limiting size. Natural selection favored larger individuals. Behavior, the art of the hunt. How did Anomalocaris actually hunt? Let's reconstruct its predatory behavior based on anatomy, trace fossils, and prey remains. Hunting strategy. Active pursuit, predator. Anomalocaris was an active pursuit predator. It searched for prey, chased them down, and captured them through speed and precision. Phase 1. Detection. Anomalocaris swam through the midwater zone, typically 5 to 20 meters above the seafloor, scanning for movement below. Those enormous compound eyes were optimized for detecting motion. Any movement in the visual field would trigger attention. Potential prey included trilobites crawling on the seafloor, soft-bodied worms, early mollusks, and other arthropods. Anything smaller than Anomalocaris was potential food. Phase 2. Approach. Once prey was detected, Anomalocaris would angle downward, undulating its lateral lobes to dive toward the target. The approach had to be calculated. Too fast and it might overshoot. Too slow and the prey might escape. The eyes tracked the prey constantly, and the brain calculated intercept angles. A sophisticated neural task requiring three-dimensional spatial awareness. Phase 3. Strike. As Anomalocaris closed within striking distance, probably 10 to 20 centimeters, the grasping appendages would shoot forward, extending rapidly through muscular contraction. The spines would close around the prey like fingers closing into a fist. If the prey tried to flee, the backward curved spines made escape nearly impossible. The more the prey struggled, the deeper the spines penetrated. Phase 4. Manipulation and consumption. The captured prey would be drawn toward the mouth. For soft-bodied victims, Anomalocaris might consume them whole or in large pieces. For armored prey, like trilobites, it would position them for optimal biting. The mouth plates would constrict around the victim, applying crushing pressure. For trilobites enrolled in defensive balls, Anomalocaris would attempt to crack the seam where head and tail shields met, the weakest point in enrollment armor. Some trilobite fossils show unsuccessful bite attempts, crescent marks where Anomalocaris bit but didn't penetrate completely. The trilobite presumably escaped, healed, and lived on, becoming a fossil that tells us about failed predation. Feeding rate and energy demands. How much did Anomalocaris need to eat? As an active swimmer, its metabolic rate was probably relatively high for an arthropod. Estimates suggest it needed to consume 10 to 20% of its body weight weekly, meaning a 70 centimeter individual would need to catch 7 to 14 centimeters of prey daily. This translates to multiple small prey items per day, several trilobites or worms, or one large prey item every few days. The hunting life was energetically demanding. Anomalocaris had to hunt constantly to survive. Swimming behavior, efficient cruise. When not actively hunting, Anomalocaris probably cruised at moderate speed, conserving energy while maintaining visual scanning. The undulating lateral lobes provided smooth, efficient propulsion without the rapid acceleration bursts needed during strikes. This cruise and strike pattern is common in modern predator sharks. Barracuda and ambush predators all use similar strategies. Slow, efficient travel punctuated by rapid acceleration during attacks. Territoriality possible but uncertain. Did Anomalocaris maintain territories? We don't know for certain, but it's plausible. Apex predators often need large hunting ranges to find sufficient prey. If two Anomalocaris encountered each other, they might have engaged in threat displays or even physical confrontation. No fossils show evidence of intraspecific combat fighting within the same species. But that doesn't mean it didn't happen. Evidence would require exceptionally preserved specimens with injuries matching. Anomalocaris appendage or mouth dimensions. Reproduction, external fertilization. Like most Cambrian arthropods, Anomalocaris probably reproduced through external fertilization. Males and females would release gametes into the water with fertilization occurring externally. There's no evidence of mating behaviors, parental care, or specific spawning sites. Reproduction was probably simple, seasonal, and opportunistic, driven more by environmental conditions, temperature, food availability than by complex social behaviors. Adaptation, refining the apex predator. Anomalocaris and its relatives showed adaptations for different hunting niches and environmental conditions. Adaptation to prey type, specialized appendages. Different anomalocaridid species had different appendage structures reflecting dietary specialization. Anomalocaris canensis. Robust appendages with strong spines adapted for capturing hard-bodied prey like Amplectovelua and delicate. Elongated appendages possibly for capturing soft-bodied worms or small arthropods without damaging them excessively. Herdia, intermediate appendage structure, probably a generalist predator taking whatever prey was available. This specialization meant different species could coexist without direct competition, each targeting different prey types. Adaptation to water conditions, depth and oxygen. Most anomalocaridids lived in well-oxygenated, shallow to mid-depth waters where prey was abundant and oxygen plentiful. But some species show adaptations suggesting tolerance of lower oxygen, larger body surface area relative to volume, more efficient oxygen absorption. Wider lateral lobes, increased respiratory surface, reduced activity levels, lower oxygen demands. These adaptations allowed some species to hunt in deeper, less oxygenated waters where competition was lower. Adaptation to changing prey defenses, arms race. As prey evolved better defenses, thicker armor, faster escape responses, better sensory detection of predators, Anomalocaris had to adapt. Stronger appendages for gripping armored prey. More sophisticated visual tracking for catching fast prey. More powerful mouth plates for crushing thicker shells. This predator-prey arms race drove continuous evolution on both sides. Neither predator nor prey could stop adapting without falling behind. The limitation, size, ceiling. Why didn't Anomalocaris grow even larger? Several factors probably limited maximum size. Respiratory constraints. Oxygen absorption through body surface scales poorly with size larger animals have more volume, more tissue needing oxygen, relative to surface area where oxygen is absorbed. Eventually, Anomalocaris would hit a size limit where oxygen supply couldn't meet demand. Structural limits without mineralized armor or internal skeleton. The soft-bodied Anomalocaris relied on hydrostatic pressure, fluid-filled body cavity for support. At very large sizes, this becomes mechanically inefficient. Energetic costs, larger size requires more food. At some point, the energy needed to power a giant body exceeds the energy available from catching prey. These constraints kept Anomalocaris below 1.5 meters below 1.5 meters seas, but small compared to later marine predators like mosasaurs or great white sharks. Extinction, the fall of the apex, Anomalocaris and its relatives dominated Cambrian seas for 20 to 30 million years. Then they declined and eventually disappeared. What happened? Phase 1. Competition from new predators. By the late Cambrian and early Ordovician, new predators evolved. Eurypterids, sea scorpions, large arthropods with powerful claws, some reaching 2 meters long, even bigger than Anomalocaris. Nautiloids, mollusks with shells and tentacles, some becoming large predators with crushing beaks. Early fish, jawless at first, but still mobile, armored and capable of suction feeding or scavenging. These competitors hunted similar prey, occupied similar ecological niches, and may have been more efficient due to better respiratory systems, more sophisticated sensory organs, or improved propulsion mechanisms. Phase 2. Prey adaptations. Prey continued evolving better defenses, thicker trilobite armor, faster swimming in mollusks, burrowing in worms. As prey became harder to catch, Anomalocaris' hunting success rate declined. Without sufficient food intake, Anomalocaris populations shrank. Smaller populations mean less genetic diversity, reducing capacity to adapt to changing conditions. Phase 3. Environmental changes. The late Cambrian saw environmental shifts, ocean chemistry changes affecting carbonate and oxygen levels, climate fluctuations altering temperature and nutrient distribution, habitat changes as continental configurations shifted. Anomalocaris was adapted to specific conditions, warm, well-oxygenated, prey-rich shallow seas. When those conditions changed, it struggled. Phase 4. The Ordovician transition. By the early Ordovician, 485 million years ago, Anomalocaris were rare. A few species persisted into the Middle Ordovician, but they were no longer apex predators, relegated to marginal roles in ecosystems now dominated by other predators. The last confirmed Anomalocarid fossils date to about 460 million years, agoraphy 60 million years after Anomalocaris' Cambrian heyday. Why complete extinction? Why didn't Anomalocarids survive in some niche? Several factors. Overspecialization. By the late Cambrian, Anomalocarids were highly specialized predators. When conditions changed, they couldn't shift to alternative lifestyles, scavenging, filter feeding, herbivory, because their anatomy was locked into active predation. Physiological constraints. Their respiratory system, while adequate for Cambrian conditions, couldn't compete with the more efficient systems of fish and other later predators. Morphological inflexibility. The Anomalocarid body plan had limited evolutionary potential there. Were only so many variations possible within the basic design. Current status, extinct but foundational. Anomalocaris and its relatives are completely extinct. No living descendants preserve their body plan, but their legacy is profound. They proved that predation was viable, even advantageous. They established predatory niches that persist today: apex predator, mid-level predator, specialist hunter. They drove the evolutionary arms race that made armor, speed, and defensive behaviors necessary. Every predator, since fish, reptiles, mammals, benefits from innovations first explored by Anomalocaris: sophisticated vision for hunting, grasping structures for capturing prey, pursuit strategies for chasing victims. Anomalocaris was the first apex predator. All others are variations on the theme it established. Anomalocaris changed the rules of life. Before predation, evolution was slow-driven mainly by resource competition and environmental change. After predation, evolution accelerated, driven by the relentless pressure of life and death. In our next episode, we'll explore another innovation of the Cambrian: the evolution of eyes. We'll see how vision developed from simple light detection to sophisticated compound eyes and camera-style eyes, and how sight transformed ecosystems by making predation more efficient and prey more aware. Anomalocaris had the best eyes of the early Cambrian, but eyes would continue evolving, becoming even more sophisticated, diverse, and powerful. The predator is established now. We'll see how prey learned to see danger coming. This is HistoPrimordia, where history comes alive. Thanks for watching. Subscribe now and join us for the next episode's story.